Imagine a connection so profound, so utterly bizarre, that two particles, separated by the vastness of the universe, could instantly mirror each other's states. Sounds like science fiction, right? What if I told you that scientists have not only observed this phenomenon, known as quantum entanglement, but that some of its reported instances defy the very fabric of our understanding, suggesting a link that shouldn't exist, a communication faster than light, or perhaps something far stranger? This isn't just about tiny particles. It's about the fundamental laws of reality, laws that, in certain experiments, seem to bend, twist, and sometimes outright break, leaving even the most brilliant minds grasping for answers. To truly grasp the unsettling nature of what we're about to explore, we first need a basic understanding of quantum entanglement itself. In the early 20th century, as physicists delved into the subatomic world, they discovered a realm governed by probabilities and paradoxes, a far cry from the predictable mechanics of our everyday experience. One of the most perplexing discoveries was entanglement. Picture two electrons born from the same event. According to quantum mechanics, these two particles can become entangled, meaning their fates are intertwined. If you measure a property of one electron, say its spin, and find it spinning upwards, you instantly know the spin of its entangled twin. Even if that twin is light years away, it will be spinning downwards. Albert Einstein famously scoffed at this phenomenon, calling it spooky action at a distance, because it seemed to imply information was traveling faster than the speed of light, a notion that directly contradicts his theory of relativity. For decades, it remained a theoretical oddity, a quirky footnote in the strange book of quantum physics. But then, experiments started proving it true. Scientists could indeed create entangled particles and observe their correlated states, seemingly defying the spatial separation. The implications were staggering. Instantaneous communication across vast distances, a fundamental interconnectedness of cosmic particles. But what if this spooky action wasn't just a quaint descriptor, but a gateway to something far more unsettling? The unraveling began with the refinement of entanglement experiments. Early tests, while confirming entanglement, often had loopholes. Perhaps the particles had predetermined their states from the moment they were created, carrying hidden instructions rather than communicating instantly. This was the local hidden variables theory, a desperate attempt to preserve a classical, understandable reality. But then came John Bell, a visionary physicist who, in 1964, devised a theorem that allowed scientists to definitively test whether these hidden variables existed. His theorem predicted that if hidden variables were at play, certain statistical correlations between entangled particles would be limited. If entanglement was truly spooky action, those correlations would exceed Bell's limit. And guess what? They did, repeatedly. In labs across the globe, from Alan Aspect's pioneering work in the 1980s to modern satellite-based experiments spanning hundreds of kilometers, Bell tests consistently showed correlations exceeding the classical limit, effectively shutting down the hidden variables theory. This meant one of two things. Either information was traveling faster than light, or our understanding of locality, the idea that an object is only directly influenced by its immediate surroundings, was fundamentally flawed. The mystery deepened with the introduction of delayed choice quantum eras experiments. Imagine you have a photon and it's entangled with another. You let the first photon travel a long distance. At the very last moment, you decide whether to measure its path or its interference pattern. The bizarre part is that this seemingly delayed choice on your part appears to retroactively determine the past behavior of the entangled photon, even if it has long since passed its point of decision. It was as if the future was influencing the past, or at the very least, our act of observation was reshaping reality in an almost unfathomable way. This wasn't just spooky, it was mind-bending, challenging our linear perception of time and causality itself. What if this wasn't just an abstract theoretical debate, but a practical demonstration of something entirely unknown, a force or principle that we've not yet even begun to catalog or name? But things took an even stranger turn when scientists began encountering anomalies, results that didn't just push the boundaries of entanglement, but seemed to outright defy explanation. Consider the hypothetical superentanglement incident based on real observations that have been downplayed or explained away. Imagine a team of physicists in a state-of-the-art quantum lab conducting an experiment with specially prepared entangled photons. Their setup is robust, shielded from all known environmental interference. They separate the entangled pair, sending one photon, let's call it Alice, through a fiber optic cable spanning a kilometer, while the other, Bob, remains in the lab. They measure Alice's polarization, a quantum property akin to its orientation, and instantly, Bob's polarization is correlated, just as expected. This is routine entanglement, but then an unexpected anomaly begins to appear. Over a series of thousands of measurements, a subtle but statistically significant deviation emerges. The correlation between Alice and Bob isn't just instantaneous, it's perfect. More perfect than physics dictates it should be, even beyond the maximum correlation allowed by quantum mechanics, factoring in the inherent probabilistic fuzziness of quantum states. It's as if a third undetectable force, or perhaps an inherent non-randomness, is influencing the outcome, ensuring a level of synchronicity that simply shouldn't be possible. The data starts hinting at a hypercorrelation, a link so absolute it suggests that not only are their states connected, but their very futures are inextricably bound beyond mere statistical probability. The lead scientist, Dr. Evelyn Reed, a meticulous experimentalist, initially dismisses it as an instrument error, a coding glitch, an environmental noise they hadn't accounted for. They recalibrate, rebuild the setup, use new detectors, move the lab to a different location within the facility, but the hypercorrelation persists. It's small, almost imperceptible to the untrained eye, but undeniably there, a persistent whisper of something wrong in the data. The probability distribution of their measurements, instead of spreading out slightly as quantum mechanics predicts, always collapses to a single point, a perfect mirror image with impossible consistency. This isn't just about faster-than-light communication. It implies a determinism that rips a hole through the very heart of quantum randomness, suggesting that these particles aren't just communicating. They're not even choosing their states. Their states are somehow forced into perfect alignment, as if by an unseen hand. The implications are horrifying to a physicist. It suggests that fundamentally, quantum mechanics itself, the most successful theory in science, might be incomplete, or worse, that there's a clandestine influence shaping the fabric of reality at its most fundamental level, an influence we have absolutely no way to detect or comprehend. They were observing entanglement, but entanglement behaving in a way that violated its own rules, a signature of something fundamentally misaligned with the accepted physics model. What could possibly cause such an absolute deterministic link in a fundamentally probabilistic universe? What Dr. Reed's team had stumbled upon, or what similar anomalies in other labs hint at, is profoundly unsettling. If quantum entanglement, a phenomenon already stretching the limits of our comprehension, is exhibiting correlations that defy even its own theoretical boundaries, then we are confronting a fundamental breakdown in our understanding of reality. This superentanglement, or hypercorrelation, suggests that either our current quantum models are drastically incomplete, or there exists an underlying, unknown structure to the universe that we've only just begun to glimpse. It could be a new, undiscovered force, a hidden dimension leaking into our own, or perhaps a demonstration that consciousness itself plays a more active role in shaping objective reality than we dare to admit. To this day, these anomalies often get filed away as experimental errors or unexplained noise, relegated to the footnotes of scientific papers. The mainstream scientific community, understandably, prefers to stay within the established framework of quantum mechanics, which already provides an incredibly accurate description of the universe. But what if these seemingly fringe observations are not errors, but signposts? What if they are whispers from a deeper, more profound reality? A reality where connections exist beyond space and time, where the very concept of cause and effect is far more fluid and interconnected than we can even begin to imagine? The universe, it seems, still holds secrets that make Einstein's spooky action at a distance feel downright mundane. If you want more mysteries that challenge the very foundations of scientific thought, the next video explores the bizarre implications of a universe that might be a hologram.